Okay, so let's recall that we have almost completed the section on Sylow's theorem, but not quite, because we did not prove the third part of Sylow's theorem. We left it hanging like this. We have seen the statement. So today we are going to finally complete everything by proving this. So before the proof, let's see the statement once more. G is a finite group and P is any given prime. That means P has already been chosen. Then the number of p-Sylow subgroups of G is of this form 1 plus Kp, where K is some non-negative integer. Now you may notice that I have just now said, or the way this has been stated, P is any prime. So P may even be a prime that actually does not divide the order of G. Let's see what happens in that case. Say P is a prime that does not divide the order of G. Even in this case, a power of P does divide the order of G, which is this. And in fact, this is the largest power of P that divides the order of G. So by Sylow's theorem, G should have a subgroup of this order, and this number is 1, and G does have a subgroup of order 1. In fact, there is only one such subgroup, which is the trivial rule, which means that for such a P, the number of p-Sylow subgroups of G is 1. And 1 is also of the form 1 plus Kp for the choice K equal to 0. So that means P actually did not divide the order of G. Such cases are also included in this. Okay, so let us now start the proof. So because of this, without any further condition on P whether it does or does not divide the order of G, we can start the proof by assuming that G has a p-Sylow subgroup, some p-Sylow subgroup P, and in the beginning of the proof we are going to consider such a p-Sylow subgroup. Consider a p-Sylow subgroup P of G. Alright, now let this be the double coset decomposition of G by P and P. Normally when we consider a double coset, we need two subgroups, but in this case both the subgroups are P. That we can do. So for P and P also double cosets can be considered, and the collection of distinct double cosets of G by P and P will form a partition of G, and this is that partition whose elements, when you take their union, you are going to get G. Okay, so that is the double coset decomposition. Now the next thing we will consider is the number of elements each such double coset has. By lemma, I'm never able to remember these numbers. 212 of course, because this is the 12th section, but it's lemma 4. We already know that this lemma tells us how many elements a double coset has, not just in this case but in general also. Okay, so we already know this. Now we are going to write numbers here in place of this expression. Let the order of P be P to the power n. Keep in mind that since P is a p-Sylow subgroup of G, so P to the power n should be the largest power of P to divide the order of G. Okay, so that is understood. And the order of this intersection be P to the power m, where m is at most n. Okay, so where is this coming from? This is coming from the fact that P intersection xp x inverse we already know is a subgroup of P. So by Lagrange's theorem, its order has to divide the order of P. So this order should also be a power of P, where the exponent, because it has to divide, this must not exceed n. Okay. Hence, so now using these things, what does this become? This becomes, you see, we will have P to the power 2n in the numerator and P to the power m in the denominator. For the sake of one particular thing, let us write the exponent like this. You have 2 n's in the numerator, so ultimately it looks like this. Okay. Now we are going to see what happens if this intersection is not equal to P. Because of these orders, this intersection is equal to P if and only if m is equal to n. So that means if P intersection x P x inverse is not equal to P, then m has to be strictly less than n. So what then happens to this? Because m is less than n, the least value that n minus m can have is 1. Okay, so it may be 1 or it may be something more than 1. Maybe 2 or 3 or something like that, but it has to be at least 1, and that is why this is divisible by P to the power n plus 1. That is, if P intersection x P x inverse is different from P, then P to the power n plus 1 divides this, means it divides this order of Pxp. Okay, but now let us also see that this condition, that this intersection is not equal to P, is equivalent to something else. Let this be different from P. Then x inverse is different from P. But let us try to understand why this is a consequence of this. What if this is not the case? What if x inverse is actually equal to P? If x inverse is equal to P, well, okay, so if this is something trivial, no? If these two are equal, then the intersection is of course equal to P. So that's why, because the intersection is not equal to P, so this is not equal to P. And there is no need for any further explanation. And so, x does not belong to the normalizer of P. Because you see, by definition, the normalizer of P consists of those elements x for which x inverse is equal to P. Okay. So if this is not equal to P, then x is not an element in the normalizer of P. Conversely, if x is not an element in the normalizer of P, then obviously x inverse is not equal to P, and so this intersection is not equal to P. Now this part needs some explanation. I am coming to that. The proof given in the text is quite clear, but there are some details that still are missing. If we see those details, it will be crystal clear. And so, P intersection x inverse is not equal to P. Unlike the implication that this implies this one is a consequence of this is not really immediately clear. Let's see what happens if we assume the negation, say P intersection, in spite of having this, suppose we are considering that the intersection is equal to P. What goes wrong then? Well, if the intersection is P, then P has to be a subset of x inverse. However, we should not forget that both of these are finite sets, and both of them have the same number of elements. We know that any finite group and its conjugate, any finite subgroup and its conjugate by an element have the same number of elements. We already know that from a previous exercise. So if you have two finite sets, one contained in the other, and both have the same number of elements, then they have to be equal. And so P has to be equal to x inverse, and that is why this inequality must imply that this intersection is not equal to P. In fact, in this part within the parenthesis, we have proved its contrapositive. So that's why we now have this. That is P intersection XP X inverse is not equal to P if and only if X is not an element in the normalizer of P. So we do understand this, and in this precise case the number of elements in this double coset is divisible by P to the power n plus 1. That let's just remember that. However, let us also see something else that happens when X is an element in NP. Let's see when X is an element in NP, what is the consequence of that? If X is an element in N of P, then by definition of this, P is equal to XP X inverse, or if you multiply on both sides by X from the right, you then get Px equal to XP. So in this case, what can you say about the order of PXP? So the order of PXP is equal to the order of, now you can replace XP by PX. So you get PPX. However, P is a subgroup, so P square is equal to P is equal to the order of Px. So we have come to know two things about the situation. Namely, if X is an element not in the normalizer of P, then P to the power n plus 1 divides the order of this double coset for that X. However, if X is in N of P, then on the other hand, this double coset number of elements in it turns out to be equal to the number of elements in this ordinary right coset of P by X. Okay, so these are two things. It may not be immediately clear that they will be of any use, but now we are going to go back to the original decomposition of G by the double cosets PXP. Using that decomposition, we can write the order of G as a sum of the orders of those double cosets, which is a usual thing. We already do, we have done such things before. Now, the order of G is equal to the sum of the orders of these double cosets, where you can see in the text that something additional is written about this sum, that this X is not going to vary freely over G, but we are going to vary this X in such a manner that one X will be taken from each double coset, distinct double coset, where, so exactly this is written in the text, where the sum runs over one element X from each double coset, and by that actually it means each distinct double coset. Now this part is, we do understand what it means, but still a little more detail would be helpful. Let R equal to just for the sake of definiteness, let us consider such a set of representatives over which we are saying that this is a sum. Be a set of representatives of the double cosets of P and P in G. What that really means is that, say you find out all the double cosets. Okay, so you will have finitely many double cosets. Say we have m number of double cosets. Now from each one of these double cosets are like some shopping bags. Each one is non-empty. There is some item in each bag. Now you are arbitrarily choosing. It's like that situation which comes up in the axiom of choice. Only the number of bags here is finite. From each one of them, without any rhyme or reason, you are just arbitrarily putting your hand inside each bag and taking out one element, xi. x1 you have taken out from one double coset, x2 from another double coset. So like that, from all the m double cosets, we have arbitrarily taken out some elements, and using those elements we have constructed this set R. We have chosen them as representatives. Okay, and this sum actually is a sum in which x varies over R. That is, in other words, you can write this sum as summation order of p xi p, where I varies from 1 to n, in that sense. Now this sum can further be split into two sums depending on whether each such representative is an element in NP or is not an element in NP. I mean, you see, you arbitrarily choose some xi from this R that either belongs to NP or does not belong to NP. So accordingly, we can write like this, order of G. First of all, let me just write, because we have chosen this, this is what it means. Now it can be written as a sum for those x in R that are not in N of P, plus a sum of order of pxp for those x in R that are in N of P. Okay, all right. I figured out why I had the problem with cleaning this board. The thing is that this room is not very well ventilated, so moisture accumulates on the board and that creates the problem. So I put it in the sun and dried it up properly, and that solved the problem to a great extent, I think. Okay, so now further we can write this like this. You see, this is going to be equal to, see, we have just now seen that if x belongs to n of p, then pxp, order of pxp is equal to order of px. So let's just write that accordingly. Summation order of pxp, where x varies over R, but those x that are not in NP, plus order of px. Now let us recall that if x is not in NP, then order of pxp is divisible by p to the power n plus 1. That was one of those two things. So that means in this sum, every term is an integer, is a positive integer divisible by p to the power n plus 1. So that means the entire term is divisible by p to the power n plus 1. In other words, it is going to be of this form, times u for some integer u, plus this for some integer, for some positive integer, actually that's understood. Okay, now next thing that is not really immediately clear in the text is that the author at once says that this sum is actually equal to the order of the normalizer of P. But why? How exactly? That we have to understand. Okay, and to understand that, I am going to add in some more detail. Let y be an element, just stay with me for some time, okay? It may not be clear why we are suddenly going, doing these things. These things are not there in the text, but let's just see where this takes us. Let y be any element in NP, that is the normalizer of P. Then yp y inverse is equal to P, that is the definition of normalizer, and this implies that y, or we can directly say something else, no? Because we have already seen how such elements behave. We can directly write this instead. If y belongs to NP, then pyp is equal to py. In fact, that's why we are able to write px in place of pxp. Okay. Is that how I have to approach? Just let me think about it for a moment. I've had the idea, but now it's gone. Py is equal to, yes, somehow I have to use this, but exactly how? Oh yes, then py is equal to pyp. This I have written just now, but note that this pyp is a double coset of p and p. Now because we know that these are the representatives, so this pyp has to be equal to pxip for some I lying between 1 and n. That's what representatives do, right? They cover all the cases. I mean, these are the distinct double cosets. So this double coset also will be equal to some one of them. So that is equal to this. Hence, you see, if you take the identity element E from P, because P is a subgroup, and consider the element EXIE, then that by the form of the element belongs to this, but that is just Xi. So Xi belongs to Py. Xi belongs to this, so Xi has to belong to Py. And that is why we can write Xi in this form. For some Z in P. Now, let us consider the conjugate of P by Xi for reasons that will be clear. Let us just go with this calculation for now. What do we get? So just simply using this expression, we get this. We know that when we take the inverse of such a product, the order changes. Now, y is an element in the normalizer. So yp y inverse is equal to p. But z is also an element in the normalizer. So this is also equal to, I think it's a bit foolish to carry out this part of the calculation, because we know that NP is a subgroup of G. So because y is coming from NP and z is also z is in P. Okay. No, not for the same reason. Okay, but then z is in P and we know that P is contained in NP as a subgroup. So z is also in NP. Yeah, this part looks quite foolish. Let's not do it like this. After doing so much group theory, we cannot do a foolish thing like this. Since, instead, let's write like this. Since P is we have Xi equal to Zy belonging to NP. Do you see the argument here? Because P is contained in NP, Z is after all an element in NP, and Y is already in NP because NP is a subgroup, so their product is in NP, that is Xi is in NP. Okay, so we have found Xi in NP. Now what does that imply? Hence, Pxi, because Xi is in NP, this is going to be equal to Pxi. That is, this Py is equal to Pxi. What does that tell us? It tells us that any element y in NP, because this y was any arbitrary element, any element in NP belongs to Pxi. We already know that any element in NP is going to belong to some right coset of P in NP. Why? Because P is a subgroup of NP. So there is a right coset decomposition of NP by the right cosets of P in NP. We already know that. Even without these things, we already know that. However, what we have found here is that any such right coset Py for an arbitrary element y which contains y actually turns out to be equal to Pxi for some representative xi. Okay. What does that mean? It means that if you arbitrarily think of this right coset Py given by any element y in NP, then that Py in the form of Pxi is appearing in this sum somewhere. That's because here we are considering Px for x belonging to R. So x is one representative. That means in considering this sum, we are actually not losing any right coset of P in NP. Each such right coset, whatever it is, will appear in some term. So let's just write that. Thus, each right coset of P in NP appears in a term of the sum of this sum. Conversely, each term in the above sum has a right coset of P in NP, obviously. Hence, so now we can write what the author has claimed. I hope it is clear why we are able to now write it. It is just this, that you have the subgroup N of P of G. Forget about G for a moment. Think of N of P as a group, and we know that P is a subgroup of N of P. Now the usual right coset decomposition of N of P by the cosets of P, one of which is P. P itself is also a coset. Using that decomposition, how are you able to write order of N of P? Using the technique that is used in the proof of Lagrange's theorem. This is nothing but the order of all the sum of the orders of all the distinct right cosets as x varies over the distinct right cosets in NP. Although I am writing like this, I am saying it the way it is supposed to be said, where x is not freely varying over NP, but x is varying over distinct right cosets of P in NP, where we take one element from each coset. The confusion that was there in this sum is that by further restricting x to lie inside R, are we losing any coset? Here we have seen that no, we are not losing any coset. So that's why this sum is actually nothing but this sum, and that's why this is equal to order of n of P. So this was the part that is missing, means the author is expecting us to figure it out, and this is how we figured it. So now what happens to our situation? So order of G now is equal to this plus order of n of P. Or order of G divided by the order of the normalizer of P is equal to, well, I should write this term first, but let's just write that term first. So 1 plus this. Okay. Now by Lagrange's theorem, since we know that the normalizer is a subgroup, so this divides this. So this is an integer, and 1 of already is an integer. So that means this has to be an integer as well. Let us give it some name. Say we call it V. This is also an integer. Now V times order of the normalizer of P is equal to this. Now because the normalizer of P contains P as a subgroup, and the order of P is P to the power n. So the order of the normalizer will be of this form. P to the power n by Lagrange's theorem has to divide this order. So P to the power n should be a part of this order. It should be a factor of this order. So this has to be of this form times alpha for some positive integer alpha. In this text, n denotes the set of all positive integers. Hence, so now what are we getting? If we substitute this expression, we are going to get V times P to the power n times alpha is equal to P to the power n plus 1 times U. Okay, now we keep in mind that since P to the power n plus 1 does not divide the order of G. See, it's coming from there, back there, because P to the power n is the order of a p-Sylow subgroup. So that is the largest power of p that divides the order of G. No higher power can divide the order of G. This does not divide the order of G, and so it also cannot divide the order of the normalizer, because otherwise by Lagrange's theorem this has to divide the order of G, which is not the case. So that means p to the power n plus 1 does not divide this. However, we already know what the form of this number is. It is of the form p to the power n times alpha. Now if p divides alpha, then one extra p will come from here and give us p to the power n plus 1, and that cannot happen. Hence, p does not divide alpha. Okay, p cannot divide alpha. Now, actually I should have written it afterwards, but anyway, this equal to p to the power n plus 1 u implies after cancellation we get v alpha equal to pu. So from this equation we can see that p has to divide v alpha, but at the same time p does not divide alpha. Now along with this you also remember that p is a prime. So because p does not divide alpha, the GCD of p and alpha is 1. So by Euclid's lemma, p would then have to divide v. So p divides v alpha, since p is a prime, or in fact you do not have to go back to Euclid's lemma. If p is a prime and p divides v alpha, we already know that p either has to divide v or it has to divide alpha. Because it does not divide alpha, it has to divide v. Thus, v is a multiple of p. But what is v? v is nothing but this. V is equal to Kp, and that's why order of G divided by the order of the normalizer of P is equal to 1 plus Kp. And now finally recall that by a previous result, this is the number of p-Sylow subgroups of G. So that's how the number of p-Sylow subgroups of G is of this form, 1 plus Kp. It is congruent to 1 modulo P, and that is the proof. So with all these things out of our way, next we can start solving the exercises, and this we will do next week. So today is Tuesday. That means our next upload is this coming Thursday. So that's just it for tonight. See you on Thursday with something new. Means you already know our schedule. So see you on Thursday. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.